In this video, we will be exploring how length, width, and depth of a discontinuity changes the amplitude of the signal. So the total volume of metal that's missing in the case of like a flat bottom hole or a pit, the length, width, and depth is what makes up the volume. And the more volume of metal that's missing, the larger the amplitude of the signal. So to demonstrate this, I have an Inconel tube. I'm going to be using an inside bobbin probe. And this tube's got a drilled support plate on one end. It's got a broached support plate on the other. And it's got a 100% through-wall hole, 80% flat bottom hole from the OD, 60% flat bottom hole, 40, 20 flat bottom hole from the OD. And then it's got 1, 2, 3 wear scars that are all about an inch wide. I don't know if you can see those. Right before you get to the support plate on the right, there's like 2 or 3 of them to the left. One of them is centered under that impedance point right there. And they get progressively deeper. So I'm going to put my probe inside of the cal standard. I'm going to start acquire on my MIZ-27. Hit null. Push the probe out the far end of the tube. Then I'm going to hit clear. I'm just going to acquire the data and pull the probe back slowly. Obviously, it wasn't balanced, right? But I'm going to go here and now hit null to bring the data back on the screen. And then, let's see here. So that's going to be your 100% hole through wall. There's your 80%. Now you may have noticed already that the amplitude of the 100 and the 80% flat bottom hole from the OD are about the same. That's because the diameter of the 100% hole is a little bit smaller. So the smaller diameter through wall hole and the slightly larger diameter 80% through wall flat bottom hole, the same metal amount or the volume is about the same. So let's go to our 60, which will be our next one. That's about the same. That's because the diameter of the 60 is a little bit larger than the 80. And the purpose of that is to make the signal size the same. So 100, 80, 60 are all about the same amplitude, because there's the same amount of metal missing from each one of those machined flaws. Then when you go down to the 40, it's much smaller. The diameter of the 40% flat bottom hole is the same as the diameter of the 60% flat bottom hole. So there's less volume of metal missing with the 40. That's why that's smaller. And for the 20% flat bottom hole, the diameter is the same as the 40. So what do you think is going to happen? It's going to get much, much smaller. So you can barely see it. It's like a half a division. So now where this amplitude is really going to become apparent is when we go on the wear scars. So these are the flaws that are about an inch in length. And there's 3 of them, each getting progressively deeper. So this is such a big flaw, there's so much metal missing that it's blowing right off the screen. So for this one, I'm going to put, well, I'll just go here and bring it down on screen with my span control. I'm going to zoom the strip charts a little bit so you can see a little more clearly what we're dealing with. There, you can see them right there. It's 3 of them, big. Each one of these is about an inch long. That's the smallest, so take note of the diameter. I'm going to actually, for clarity, I'm going to bring it down even more. I'm reducing the amplitude, and I'm going to hit data cursor. So there's the smallest of the 3 wear scars. That's the next deepest one, so that goes right off screen. And the third one really goes off screen. So what we'll do is I'm going to bring the span down even more. So this is going to be the largest of the 3. Okay, so I get that one totally on the screen. And now when I go down to the other two, that's the medium one, medium depth. Make my window a little bit bigger here so you can see it. And that's going to be our smallest wear scar. So you can see how the volume of metal missing contributes towards the voltage or the size or the amplitude of that signal, whatever you want to refer to it as. Now, to size these types of indications, a lot of times they'll use a mix. And I have already created a mix for this channel. And what you normally do with the wear scars, I'm going to put a mix channel 2 up here. Mix 2 vertical, okay. We normally take those flaws and we vector them upwards, up vertical. I need to increase my span so you can see that one. So that would be, oh, it's probably about a 20% wear scar. And then when we go up to the next one, it's going to go off screen. That's 60%, 40%, I mean. Then the next one's going to be 60%. So I'll bring this one back down on the screen using my gain control here. So that's 60%. Now this is an absolute mix, right? So that's 60%, 40%, and that's the 20%. So here you can clearly see, whether you're looking at absolute channels or differential channels, the total volume of the material that's missing is what is going to determine the amplitude of your signal. More metal missing, bigger impedance change, larger signal. So oftentimes, signal amplitude or voltage can be used to size the severity of flaws. End of video.